when you do studies that look not at meaningless, simple geometric forms, but at the use of shape information to recognize objects. You find that we use length relationships, we use angular relationships. We don't use the distinction between a shape and its mirror image. And we also primarily use information at corners, not extended surfaces. Take away the middle of extended surfaces and objects tend to still be recognizable. Take away the corners and they're not. Just the opposite of what you see in the navigation situation. So it looks like we've got evidence for two systems that are behaving very differently. A navigation system that cares about distance but not length, and a form analysis system that does the opposite. Similarly for sense and angle, and one system that cares about continuous surfaces, the other that cares about corners. And I think this suggests two general conclusions. First, that we've got evidence for two distinct systems of core geometry. Our Euclidean intuitions seem to be unitary, but what we seem to see here is a breakdown into two distinct systems. But second, I think we can see that if we had some way of combining the information from these two systems, we'd be able to get something more powerful, something that captures all of Euclidean geometry. Now, it's convenient that I'm out of time now. I can't tell you about the research that we are in the midst of that's asking how children do this. Let me quickly point to it, though, to get to my conclusion. How could these things be combined? Well, since the Munduruku can do it, but they haven't been to school, it must be through some experiences that you can get on your own. What are the experiences that Munduruku share with us that could serve as a basis for combining information from these two systems? Well, one thing they share is they, too, have a natural language. And second, they make pictures. They make geometrical patterns all over the place, including on their own bodies. And they draw pictures in the sand and make pictures of the world around them, as do people in every human culture, suggesting that abstract geometry might emerge as we use language and pictures to combine these two very different kinds of representations. And there's research showing that language plays a role, at least in the simple navigation tasks where you have to combine information about the shape of a room with information about the crisscross panel in a room corner. Language allows us to do these things in two ways. First of all, we have words, like triangle, that apply both to the shapes of large-scale layouts and to the shapes of objects. And second of all, we have rules for combining words into expressions that let us say things like left of the corner that's got crossing lines on it, right? Where you're combining the left-right relations that one system captures with the form relations that the other system captures. And there's evidence that as children gain spatial language, they start to use this ability to navigate in new ways. Finally, this is the most speculative part, but I think pictures are especially interesting because within one and the same picture, you typically see representations both of objects and of extended scenes. And the functions of lines and pigments and surfaces on a picture are the same regardless of whether what's being represented is an object or what's being represented is an extended surface. And interestingly, if you look at line drawings, those lines are related to the thing that they're representing extremely abstractly. So Leonardo da Vinci's lines here are representing this body, but the body doesn't have a line at it, at the position where that line is. That line is showing you the tangent where the body goes from being visible to being invisible as it curves around. That's a very abstract property. In fact, it's a property of a line that has linear extent but no thickness, an abstract object of formal geometry. Maybe as kids come to understand pictures as symbolic media, they pick up on this abstract function. I'm not going to tell you where we've gotten in pursuing that suggestion. Let me just conclude. I started out with three general questions. What's special about us as a species? Where do our abstract ideas come from? How can we change our minds and gain new concepts that are more powerful? I suggested first that the answers to this question partly reside in two core systems of geometry that begin to develop in us and in other animals in the absence of any experience, and that we use to perform basic tasks like getting around in the environment and knowing where we are, or recognizing objects based on their shape. These systems capture truly geometric information. As I said, they're functional from birth, but they're limited. They capture some geometric properties, but not others. They apply to some kinds of things, but not others. And they're shared by other animals. They can't be the whole story about what's special about human intelligence. But I think we also have symbol systems, most especially systems like language and visual spatial symbols that could serve to take the outputs of these two systems and connect them. And I think these systems do have the right properties to serve as a basis not only for abstract Euclidean geometry, but for many, perhaps all, of our uniquely human accomplishments. First of all, these symbol systems are unique to humans, and they're universal across human cultures. That would be the first requirement of something that's going to provide the answer to what's special about us as a species. Second, they represent the world abstractly, in ways that we can understand, but not because anyone can point out that relationship to us. And third, and I think most important, these are productively combinatorial systems that we can use not just to learn new concepts one by one, but to construct whole new systems of knowledge and families of concepts. Now, if you followed me this far, and if you're intrigued by the possibility that future work could actually shed further, deeper light on these kinds of questions, then there should be a lot of questions in your mind. Here are a few of them. How does each of these core systems work? I've told you that they exist. I've shown you some of the places where they succeed and fail. But what are they actually computing? And what systems in the brain are engaging in these computations? And how do those systems develop and grow and function? Second unanswered question, how do children master new symbol systems? How do they come to figure out that pictures represent the world? Incidentally, that's something that very young children do not seem to know. How do they come to work out how language works? How do they come to see language, words, as symbols for things in the world and as things that can productively combine to yield new expressions? How, by linking these different geometrical relationships together, do children actually get to new geometrical concepts that go beyond the power of the concepts with which they began? And finally, and maybe most importantly, why does it take children so long to learn these concepts? And what, if anything, might we be able to do in order to foster their learning, in order to make understanding of geometry something that feels as fun and natural and intuitive to children as the kinds of abilities that they show when they simply navigate through space or look at and analyze visual forms? I didn't say this during my talk, but children find those tasks easy and they love them. Often, though, when kids get to school, they find their improving in geometry to be boring and tedious and meaningless and all of that. How do we bridge this gap to make these subject matters both more accessible to children and more engaging in the sort of way that they do become for mathematicians and some lucky people among us? Well, as I say, I think these questions are all entirely outstanding. They should be the subject of future work. But the one last thing I have to say that I think cognitive science today provides is a whole set of methods that can be used to address them. Thanks.
Thanks, Liz. That was great. She's already given us a lot of questions, and maybe you'd like to discuss with her the answers to some of her questions, or maybe you have your own questions for her. So let's hold off on those until the end of the session. We're going to have a question and answer session a little bit later. But before then, I'd like to now introduce our next speaker, Professor Leher Singh, who's a member of the faculty of the Department of Psychology at NUS. Before coming to NUS, she was at Boston University in the United States. Professor Singh's work focuses on early word learning. She's interested in the influences of variability in word recognition and in novel word learning in infants and toddlers. Her work examines early memories for words with a particular focus on influences of emotion and other factors on the emergence of word knowledge. She also studies language and cognitive processes associated with multilingualism. So I'd like to welcome Professor Singh to present her talk on early language development in infants and toddlers.
Okay. My talk is entitled Early Language Development in Infants and Toddlers. And here's a picture of my infant and toddler who re-educate me on a daily basis about language development in infants and toddlers, and also about bilingualism, which is also the primary focus of my research program. So I got into cognitive science and I got hooked on language development when I was in college, and I read a book called The Language Instinct by Steven Pinker. Like many cognitive scientists, I was entranced by this book. And even though that was, 22 years ago, what stayed with me about this book and what continues to sustain my interest in this field is the contradiction between how effortlessly and automatically children seem to pick up language and the decades of empirical research dedicated to try to understand how this kind of rapid and efficient learning is possible. So I just want to situate what Liz said within the field of language and reiterate that there are more questions than answers in this field, but due to the sort of rapid, continuous evolution of the field, especially in terms of methodology, it seems like there are promises of some answers to some very fundamental questions. So, of course, I think it's a fascinating field, but I also think that this is a fascinating time to join the field for that reason. When we think about how children acquire their own language, we can think of this in terms of different tiers of language, in terms of acquiring sound patterns, acquiring words, and acquiring phrases, larger units. And my research is primarily focused at the word level, but of course all of these levels of the language code interact with each other. And I spent, after I finished my doctorate, I spent 10 years in Boston, at Boston University, where I mainly did research on language development in monolingual infants. And since moving to Singapore, I've changed the focus of my research to look at different language typologies, so specifically to look at the acquisition of lexical tone, one of the features of Mandarin Chinese. So most of what we know about language development is based on language development in Germanic languages, but most of the world speaks a language where there are different kinds of phonetic segments. So most of the world's languages are tone languages, where changes in the pitch contour of a word actually change the meaning of the word. But we know very little about how these kinds of systems are acquired. And secondly, most of what we know about language development is based on the monolingual child. But most of the world is born into a multilingual environment. And as the sort of picture of a multilingual child comes into focus, we can see there are some very fundamental differences quite early in life that differentiate monolingual and multilingual children. So I want to talk about what some of the challenges and complications are that a multilingual child faces, and what are some of the potential benefits of growing up in a multilingual environment. So Singapore, I think, is a natural laboratory to look at these questions. It's impressively multilingual. So I want to talk a bit about what are some of the challenges that early learners face. So when we think about word learning, one of the most fundamental challenges is how do you find the words? Where are the words in the speech stream? So this challenge is called the segmentation problem. When we speak, we don't stop at the end of one word and then start speaking when we want to start a new word. Words run into each other, and speech is a continuous stream of information. And it's for us to carve up that stream into these very important discrete units, given this continuous stream. So you can see an illustration of this where there are apparent breaks in the signal where there aren't necessarily word boundaries, and there are word boundaries where there aren't apparent breaks in the signal. Another way of thinking about this is if you go to another country where you don't know the language, it's very difficult to know or to figure out where words